Welcome to Grade 11 Artificial Intelligence. You have learned to use AI, but where does new AI knowledge come from in the first place? Every model, every method you have studied began as someone's research. In this module, we learn how that research is done and what separates a real finding from a lucky number. Here is our plan for the module. We'll see where AI knowledge comes from. We'll walk the research process from end to end. We'll meet datasets, benchmarks, and baselines, then reproducibility and ablation studies. We'll cover experimental design and a little statistics, and finish with writing, peer review, and ethics in research. Let's start with where AI knowledge actually comes from. It is not handed down by authority, and it is not just clever opinion. Researchers propose an idea, then test it with careful experiments. When the evidence holds, they publish a paper openly so others can read exactly what they did. Then other teams build on that result or challenge it by trying to repeat it. This is how the whole field grows, by evidence that anyone can check, not by who said it. To produce evidence like that, we follow a clear process. Every AI study moves through the same 6 stages. First, a question. Ask something worth answering. Second, a review. Read what is already known so you don't repeat solved work. Third, a hypothesis. State a clear, testable prediction. Fourth, the experiment. Design a fair, controlled test. Fifth, analyze. Measure the outcome and check it is significant, not noise. Sixth, communicate. Report it so another team can repeat it. And this is a loop, not a line. Each answer raises a sharper question, and the cycle begins again. Let's look at the materials a fair experiment needs. A fair experiment needs 3 things. First, a data set, the examples a model learns from, and a separate set it is tested on. Second, a benchmark, a shared dataset and task that everyone reports on so results can be compared fairly. Third, a baseline, a simple, honest reference that a new method must beat. Why a baseline? Because a number on its own means nothing. Saying a model scores 90% is empty until we ask 90% compared to what? Real progress means beating a sensible baseline on the same benchmark under the same rules. And once we have a result, we must show others can repeat it. A finding only counts when another team can reproduce it. So we release the code, the data, and the exact settings we used. We fix the random seeds and report them so the same run gives the same numbers. Then comes a powerful technique called an ablation study. We remove one part of the system and measure how much the result drops. For example, if removing the data augmentation makes accuracy fall from 88 to 83, we have learned exactly how much that part contributed. Reproducible, well-ablated work is what lets the whole field build forward with confidence. Now, how do we know a result is real and not just luck? Good design starts before any model is trained. We split the data once into a training part, a validation part, and a held-out test part. We tune and choose our model on the validation set only and never touch the test set while developing. Then, because one run is not evidence, we repeat the experiment over several random seeds. Suppose the network averages around 88% and the baseline around 81, each with a small spread. A significance test gives a p-value of 0.002, meaning a gap this large would rarely happen by chance. And the gain, about 6 points, is large enough to matter in practice, significant and meaningful. Good research needs both. When the result is solid, we write it up. The next stage is writing the work up and putting it before others. A paper states the question, the method, the results, and the limitations, so a reader can follow and judge it. Before it is published, it goes through peer review, where independent experts check the claims for flaws. We report the limitations and even results that did not work, rather than hiding them. And we cite the prior work we built on, giving credit and helping readers trace the ideas. Honest reporting and careful review are what keep the field trustworthy. There is one more responsibility we must never set aside: ethics. Ethics shapes how research is done, not only what it finds. Integrity comes first, no plagiarism, and no fabricated or cherry-picked numbers. When the work uses people's data, we get consent and protect their privacy. We check the findings for bias, and we think about how they could be misused. And we are honest about the limitations and about any conflicts of interest. Research that is dishonest does not just fail, it pollutes the knowledge everyone else builds on. Let's see fair method at work around the world. Good method looks the same everywhere, even when the labs look very different. In Rwanda, a crop disease model is tested on photographs from farms it never saw in training, so the score reflects the real world. At a university in the United Kingdom, a team registers its hypothesis before running anything, so it cannot quietly change the goal afterward. On a benchmark leaderboard in the United States, a hidden test set ranks every model on exactly the same unseen data. The rule that unites them all is the same. Test only on data the model has truly never seen. Few traps turn a promising result into a mirage, so let's name them. First, data leakage, tuning on or even peeking at the test set, which secretly inflates the score. Second, reporting a big number with no baseline. Without a reference, it means nothing. Third, claiming victory from a single lucky run instead of averaging over several. And fourth, confusing statistical significance with a meaningful effect. A tiny gain can be significant yet useless. Avoid these four, and your findings will hold up to scrutiny. Let's gather the key ideas. AI knowledge grows by tested, openly shared evidence. The process is a loop. Question, review, hypothesis, experiment, analyze, communicate. To claim something is better, use a benchmark and a baseline. Make the work reproducible, and use ablations to test which parts matter. A result should be both statistically significant and large enough to matter. And throughout, write honestly, welcome peer review, and keep ethics first. Now let's check your understanding with 3 quick questions. Here is the first question. A team reports their new model reaches 90% accuracy. What must they compare it against for that claim to mean anything? On its own, 90% could be worse than a trivial model. They need a baseline on the same benchmark, so the comparison shows what beating it really means. Question 2. To find out how much the data augmentation step contributes, a researcher removes it and measures the result again. What kind of study is this? Removing one part and measuring the drop tells us how much that part mattered. This is an ablation study. Last question, and it brings our ideas together. Model A beats Model B by only 0.1% with a p-value of 0.001. Is this a strong result to publish? The tiny p-value shows the difference is real, not chance. But a 0.1% gain is too small to matter in practice. Significant is not the same as meaningful, so this is a weak result. Wonderful work. You now know how AI research moves from a sharp question and a falsifiable hypothesis through a fair experiment with a baseline to a significant, reproducible, honestly reported result. You can read a paper critically and you can begin to do research yourself. In the next module, we put AI to work on one of the biggest challenges of all and explore AI for climate and the environment. I'll see you there.